Welcome to the Explainer. So, today we're going to demystify something that sounds, well, incredibly complex, but is actually a fundamental part of our everyday lives. We're talking about computational thinking. I'm going to show you how the exact same mental models apply to everything from, writing complex software code all the way down to simply cooking your morning meal. All right, let's just dive right into it.
Think about this for a second. How exactly do we bridge that massive gap between human intention and machine execution? Like, how do you tell a literal bundle of wires and sensors to follow a line on the floor? Or, for that matter, teach a huge banking system to calculate a 30-year mortgage instantly? Well, the answer to both of those questions lies in computational thinking. It's essentially this structured way of breaking down the world around us so that we can solve problems efficiently and, more importantly, reliably.
So, here is our roadmap for today. We'll start with the problem-solving process, then move on to defining the problem scope, explore the input-process-output cycle, look at decomposing complex problems, and finally, finding patterns and solutions.
Okay, Section 1, the problem-solving process, the 6-step roadmap.
What's really fascinating here is how this formalizes something we honestly do subconsciously all the time. Check out this 6-step problem-solving flowchart. It all starts right at the top with problem definition, where we figure out what we actually need to do. Then, we move into problem analysis, looking at how systems interact with users. From there, we jump to algorithm design, mapping out every single step. And only after all that planning do we actually get to step 4, program development. That's where the actual code is written. But we're not done yet. Step 5 is testing and debugging to catch any of those pesky errors. And finally, documentation, where we just use everyday language to describe how the whole shebang works so it can be updated later. It's this brilliant, totally linear path from an abstract idea to a working solution.
Moving on to Section 2, defining the problem's scope, preventing failure.
Right, so the absolutely crucial takeaway here is that defining the scope prevents catastrophic failure. We use thinking tools for this, like the 5W1H method. Who, what, where, when, why, and how, or even just mind maps to branch out our ideas. Just consider this scenario for a minute. A boss tells their IT manager to set up a website for their coffee shop. If that manager just starts coding right away without defining the scope, they are practically doomed. They need to ask, are we selling bags of coffee beans to be shipped globally? Or are we taking online orders for hot lattes to be picked up at the counter in 5 minutes? Because those are two entirely different programs. Defining the scope really is the absolute bedrock of computational thinking.
Next up, Section 3, the input-process-output cycle.
The IPO cycle breaks down into 3 distinct, highly sequential phases that really guide how a program reads and returns information. First up, we have the input, which is basically the raw data or materials being used. Second is the process. That's the actual method, calculation, or procedure performed on that data. And third is the output, the final information or result returned by the program. Honestly, pretty much every digital action you take follows this exact rhythm.
And what's super cool is that the IPO cycle isn't just for computers. It applies to incredibly relatable, everyday tasks. Take this example of brewing coffee. What are our inputs? Well, adding coffee powder and adding hot water, right? And the process? That's the active phase, the dripping of the water through the filter. And then what's the output? That glorious act of pouring the finished coffee right into your cup. Input, process, output. It really is that simple. Now let's actually connect this back to our initial question. How does a robotic car manage to stay on a track? Well, it uses the exact same IPO cycle we just used to make coffee. The car has these infrared transmitters and receivers on its left and right sides. The input is simply the data detected by those sensors. If the sensor detects a black line on the left, but nothing on the right, the process is the algorithm analyzing that data and concluding, the car is tilting too far to the right. The output is then the command sent directly to the motors to turn the car left, bringing it right back onto the line.
All right, Section 4, decomposing complex problems, stepwise refinement. This brings us to an awesome top-down approach known as decomposition and stepwise refinement. Decomposition simply means breaking a massive, super intimidating problem into several smaller, highly manageable subproblems. It is the ultimate divide-and-conquer strategy. And stepwise refinement? That's the process of continually breaking those modules down further and further until they're simple enough to solve effortlessly. I promise you, when you master this, literally no problem is too big.
Let's imagine your main problem is making a huge all-day breakfast. If you try to do everything at exactly the same time, you're going to burn the food, right? So we use decomposition. Our first step of refinement breaks this giant problem into 4 submodules: make baked beans, make a toast, brew a coffee, and fry an egg. But actually, we can go even deeper. Just look at the make a toast module. Our second step of refinement breaks that down into slicing the bread, toasting the bread, spreading the butter, and spreading the jam. By chopping the overarching problem into these tiny little steps, you can program or cook with absolute precision. Moving into Section 5, finding patterns and solutions, the bottom-up approach.
So, after breaking things down, a really smart computational thinker will immediately start looking for similarities to save time. Here, we've got block code in a program called Scratch designed specifically to draw a triangle. It repeats a movement 3 times and turns 360 divided by 3 degrees. But what if we want to draw a square, or a pentagon, or a hexagon? Do we really sit there and write entirely new code from scratch every single time? No way! We use pattern recognition to create a generalized program instead. By just changing one tiny variable, the number of line segments, we can draw absolutely any regular polygon using the exact same block of code.
As our source material beautifully points out, with pattern recognition, we can fine-tune existing methods to solve more problems easily and significantly reduce the time needed for seeking new methods. This is what's known as a bottom-up approach. You're basically identifying similar, smaller issues, grouping them all together, and creating one unified solution to tackle a much larger problem. It makes programming incredibly fast, and honestly, a lot less of a headache.
Let's try applying this bottom-up pattern thinking to an algorithm you probably actually ran natively as a kid. Imagine a PE teacher needs to sort a whole class of students from shortest to tallest. The algorithm goes kind of like this. Step 1, list all the heights. Step 2, identify the shortest student and put them in first place. Step 3, look at the remaining students, find the shortest among them, and put them in second place. Step 4, just repeat this identical process over and over until the entire line is perfectly sorted.
And boom, here we have our output, a perfectly sorted lineup. Now, the true power of these generalized solutions is that we can tweak this pattern so easily. Like, what if the teacher suddenly wanted to sort the students by descending order of weight? We don't need to invent a brand new algorithm. We literally just change the variable in our pattern from shortest height to heaviest weight, and we run the exact same iterative process. Identify the heaviest, put them first. Find the heaviest remaining, put them second. The core logic is just universally applicable.
Finally, let's talk about taking it from behind the scenes to the user interface.
You see, when developers create wireframes and user interfaces, they rely entirely on that IPO cycle we talked about earlier. Just look at this simple body mass index or BMI calculator interface. You have text box 1 for weight and text box 2 for height. Those are our direct input components. Then you have a calculate button, which triggers the actual process component. And finally, you have a text label at the very bottom, which serves as the output component to display your BMI. It's wild to think about, but every button, every text box, and every drop-down menu you interact with online is really just a visual wrapper for the input-process-output cycle. So, as we wrap up this explainer today, I want to leave you with a bit of a provocative thought. We've seen how defining a problem, utilizing the IPO cycle, decomposing large tasks, and recognizing patterns are the total bedrock of computer science. But we've also seen them applied to brewing coffee, making toast, and lining up in gym class. If so many of our daily activities are basically just algorithms waiting to be run, what other habits and routines in your own life could you systematically optimize by thinking like a programmer? Definitely keep that in mind the next time you tackle a complex project. Thanks so much for joining me on the explainer today, and hey, keep thinking computationally.